let's talk about completing the square. Yes, that dreaded mathematical trick that literally no one knows how it works. Not one. How to complete the square is the primary objective, sure, but how completing the square works is far more interesting to me. So, first question. When do we complete the square? We complete the square when we're looking at something like x squared plus bx plus c equals 0. And we can't, for the life of us, figure a way to factor that left side. So, to work on this, let's ignore that plus c equals 0 for a bit and focus only on the x squared plus bx. X squared kinda sounds like we might want to look at an actual square, say one with side length x. That way, its area is exactly that, x squared. In that case, we ought to treat the bx like it's a rectangle, seeing as the x doesn't have to be the same as the b. So, the length of the rectangle will be x and the width will be b. Great. So now we have a square and a rectangle. Let's talk about something else for a moment. If we look back at something that looks like, say, alpha plus beta all squared, we expand it by doing this crazy multiplication thing and get alpha squared plus 2 alpha beta plus beta squared. Okay, so why'd I do that? Currently, I have something that looks suspiciously like that alpha squared plus 2 alpha beta, but there's no 2, and there's no beta squared. We'll get there. So let's split this rectangle in half, the bx rectangle. That way we have 2 of them. Each smaller rectangle now has a length of x and a width of b over 2. So what? Well, we can take those smaller rectangles and attach them to the sides of our square. Now we have what could be a nice clean square, if not for that obnoxious space in the top right corner. Why not let's extend the sides of these 2 rectangles and make a nice clean square anyway. This step is the reason we call it completing the square. We set up a nice square, then we add a piece that completes it for us. So now we have a new piece to add onto our original equation. We're going to add and subtract the area of our new little square. What was that area anyway? Well, if we look at the drawing, the little square has side lengths b over 2, so the area is b squared over 4. So let's add and subtract that to the equation. Wait, why are we adding and subtracting? Doesn't that just do nothing? Here's the thing. We have just done nothing in a very creative way. The piece we added, we're going to group with x squared and the bx. If we look at that for a moment, it doesn't mean much to us, but we can rewrite it by using the setup from our nice big square. It looks kind of like x squared plus 2 b over 2 x plus b squared over 4, which, if we look back to our alphas and betas, has the same structure. But that means this new group should factor. It should factor nicely to the side length of our square, except squared. That side length we can see is x plus b over 2. So now we have x plus b over 2 all squared minus b squared over 4 plus c equals 0. So, let's say we want to use this to solve an equation. We can do it pretty easily. Let's have a look at this example. Let's say we want to solve x squared minus 6x minus 5 equals 0. We ignore that minus 5 equals 0 for a moment and focus only on x squared minus 6x. We can then put these numbers into our nice square, and we see that the missing piece has area 9. Then we add and subtract that 9 to our original equation. That way we get x squared minus 6x plus 9 minus 9 minus 5 equals 0. We split off that first part, just like before, and factor it easily using the square. x minus 3 is the side length, so the area is just that squared. Combine the minus 9 and the minus 5 to get minus 14. From here we can move that to the other side by addition. Now we have something that we can just take a square root of. But we gotta make sure when we take the square root of a square, we have a plus or minus. Then add that 3, and our equation's been solved. There! That's all there is to it.